Hello everybody, thank you to be there for this presentation. Thank you to the organization of Barcamp 11 to invite me. It's amazing to be there, and the event and its program is really amazing. I'm really happy to be there. So the topic of this presentation is to try to explain key concepts to understand quantum computing and being able to begin to really program with quantum computing. And it's not difficult actually, but you have to know 2 or 3 concepts from physics to not difficult but a bit strange actually, counterintuitive. And it's the goal of this presentation to give the basis to be able to do something with quantum computing. Perhaps some of them already did some stuff with quantum computing? Yes? Yes, not a lot? With which platform? With IBM, you mean? Yeah? Okay.
You found one good.
Yeah, one guy, yes. Yeah, tell me if I say some wrong stuff. Do not hesitate. So, quantum physics, actually, it's the base for quantum computing. Actually, quantum computing use the behavior we can only observe in the quantum world. And quantum world is the world of the infinite small. It's at the particle level, actually. So there is a huge difference between our world in terms of mechanics, and we have intuition about that. If I take this object and if I throw it, and everybody here has the intuition, it is going to make a noise, perhaps it will be broken, I don't know. And because we have the intuition of gravity. And we don't have any intuition of the quantum world. And so it's a bit a difficulty. And the second point, there is a connection between this world and our world, if I can say. And we will see that much later. And the big point is our world is determinist in terms of mechanics. If I have every hypothesis, for example, with this object, I throw it. If I have everything, the force on this object, the time, every data, I can clearly predict where is going this object when I throw it. It's deterministic. At contrary, the quantum world is totally probabilistic. It's a question of statistics. So it's also counterintuitive. So the topic here is not to talk about physics, but we are at an atomic level or subatomic level. So just a small reminder you probably have. But in an atom, we have a nucleus. In the nucleus, you have neutron and proton. Proton are with a positive electrical charge. Around this nucleus, there is electrons, one or several electrons, depending the particle, and it's obviously negatively electrically charged. And I provide another precision about light because it's quite deeply used in quantum. It's about light, yeah, and the photon. Just for a reminder, the light is a wave. We know that for centuries now. But it's also matter, actually. And the matter in light is photon. And a quite large part of attempt to build a real quantum computer is based on photon. So it's the reason I precise that here. And yeah, I wrote wave-particle duality because there is two aspects. There are two aspects in the light. An aspect wave, but it's not exclusively wave. It's also matter, particles, and these particles are photons. This slide is to present the first counterintuitive phenomenon and also to explain the etymology of quantum. And perhaps you learned that during your studies, probably. And it's about the absorption and emission of electron in the atom. Actually, there is quantified level of energy to change the position of the electron. You have to solicit the exact quantum of energy to change the level, and it's really counterintuitive because in our world it doesn't work like that. We don't have any restriction in terms of used energy to change something. And this level of energy is named quanta, and it's the etymology of quantum. So quantum physics is the physics of the very small world, and the quanta is from this notion of level of energy. Oops, sorry. Before to continue, I guess to be able to begin to work in quantum computing alone as soon as you can, you have to get three concepts, not very complicated, but it's the key concept you have to know actually. It's superposition, measurement. These two concepts are connected quite strongly, and entanglement. Entanglement. In French, there are two words for entanglement, and in English only one. In Armenian, I don't know actually. What is the translation of entanglement? We will see that much later. Perhaps you know this principle, Heisenberg uncertainty principle. Heisenberg is the name of this physicist, and it's the reason perhaps you saw Breaking Bad, and in Breaking Bad the hero, the nickname is Heisenberg. He's come from this guy, this physician, physicist, and. Heisenberg explained that if we know precisely a characteristic of a particle, we cannot know another characteristic. For example, if we know the position of a particle, of a given particle, we cannot know its speed. And the reason of that, there is something about superposition, and we will see much later, about measurement of data, actually. And the main reason is that as soon as we try to pay attention about a value, it changes the value. It's totally counterintuitive. In the real world, if the police try to measure the speed of a car, it doesn't change the speed of the car. In the quantum world, it's going to change something. We'll see exactly what is it, but it's the first point to get superposition and measure, etc. And it's quite well explained by this mind experience, if I can say. Probably you know. Schrödinger's cat, and basically the purpose of this mind experience is it's quite cruel. It's to put a cat in a box in a black box actually. And there is a device, a cruel device here. It's present, and it can be activated at any time. We don't know when it's going to be activated. So from outside, we cannot know if the cat is alive or not. We can see that like the cat is in the same time alive and dead, because the present can be activated at any time. In the box, it's the quantum world in this experience. We are in the quantum world, and the state of the cat, it could be a particle, the state of the particle, but the state of the cat is dead plus, is perhaps 50% dead plus 50% alive. And when we open the box, it's the measure. We come back in the real world without superposition. It cuts totally the superposition. And at this time, the cat is either alive or dead. In my example, I did the choice to have the cat alive. It's better. And in this second picture, we are in the classical world, in the classical mechanical world, our world. In the box, inside the box, it was in the quantum world. It's metaphor to try to explain the concept of both superposition and measurement. This slide was not so useful. It was there only to explain that we can see things like symmetry between real world and quantum world. In classical mechanics, we have the Newton's law of motion. It's totally deterministic. If we have all the hypotheses, we can explain every movement, everything in our world. We have a kind of similar global principle explaining everything. In quantum, it's the Schrödinger equation, and this notation here could be translated in natural language. It's quantum state of this particle at a given time, but we don't care the time here. This bracket, the name of that is bracket of Dirac notation, but much frequently bracket notation. It means quantum state, so before measurement, quantum state of this particle. So we have that Schrödinger cat, superposition in the quantum world. We can interrupt superposition with measure, and when there is a measure, we are in the real world. We cannot be both dead or alive. It's one of them. And to be much specific, I did this rhetorical example. Actually, we have a particle, and we try to be interested by its speed, actually. And in my example, the quantum state in terms of speed is 25% of possibility is a first speed, speed 1, plus 45% speed 2, and 30% speed 3. At the left, we are in the quantum world. The particle is going as own speed composed by this combination of three speeds. There is a measurement, and this probability is the probability to be the selected speed after the measurement. In my example, is speed 1. So we can see superposition like a combination of several values with probability to be the winner of the measure after that. Here we are in the real world, actually. Here we are in the quantum world. And to be a bit much specific, so bracket notation means quantum state, actually. And if I have only one qubit, a qubit is the representation of the quantum state. And in our world, a bit, a computer bit is 0 or 1. But in the quantum world, we have the possibility to have superposition. So the quantum state with only one qubit, look for only this line, not that. When I have one qubit, I have a probability A to have the state 0 plus the probability B to have the state 1. Plus here symbolize the superposition. We have the two states in the same time. So at this time, we can see that in our world, a state of a bit is 0 or 1. Only with one qubit, we have two values. We have something like a combination, something related to combinatory stuff, actually. And if I have two qubits, you see the combination is much relevant. We have 4 possibilities. So it's a combination of 4 states before measurement. With 3 qubits, it's 8 states, like that. So it's 2 per number of qubits. And if you are aware about stuff like operation research and combinatorial problem in industry and stuff like that, you can feel what is the reason of the current success of quantum computing, because it can be used to focus to try to propose solutions to very difficult problem, NP problem, for example, in operation research. And it's not able to provide an exact solution, but it can give already today better results with heuristics to get an approached solution. Better results in terms of time complexity, in terms of time of resolution. So in our world, electronics, etc., we have bits 0 or 1, and you are aware of this kind of gates to make electronic circuits. For example, this one is the NOT gate. And there is the same concept in quantum computing. So we can have in input some qubits, some quantum state of particles, and we can change the superposition. We can use this kind of quantum gates. We will see just after this one, for example, to change the situation of superposition. And for example, these 2 famous quantum gates, Hadamard gate and the C0 gate here, they are something like 60 or 70 gate type of quantum gates. And this gate is special, is the measure. So the capability on a qubit to get the value, actually, and to get a 0 or 1 and not a superposition. For example, we have this, it's an example of quantum circuits using few quantum gates, Hadamard gates 3 times, and we have here outputs, and we can do a lot of things with that. A word about the distinction between quantum simulator and quantum computer. Quantum computer is real quantum computer, actually. It's physics, and we try to manage a physics machine to have a real computation. And for example, we have the idea to use the photon polarization, the electron speed, the state of the particle which is interesting for us is electron spin, for example, to have the 0 or 1. Cold atom is very used, and in that case, the quantum state is energy levels, we discussed before. But we still are in the domain of research, actually. Very big companies, big laboratories, Google, etc., try to have something relevant and to improve the number of qubits. And there is another version of quantum machine. It's quantum simulator. It simulates the superposition on a regular computer, but it can be a HPC, a supercomputer, actually. So you can have quantum behavior on a classical machine, and this stuff is still not in the field of research. It's already in the field of business. Actually, you have some companies able to provide consulting, to tune quantum algorithm, to answer industrial questions, and to run this algorithm on very big computing simulators. It needs a lot of memory. For example, to have only 30 qubits, you need 16 gigabytes, so it's quite, it needs a lot. And the connection between these simulators or real computer and you is quantum frameworks, and the main big players in the computing domain. Everyone has its framework. For example, Qiskit is from IBM. There is Microsoft Quantum. There is Circ, Google. There is IQSM. It's from Atos. It's European and a bit French, or you. And you have a large offer to use. It's free. And there is a lot of interconnection among this solution. So you can begin by IBM and try to use it with the Atos simulator. It's possible. Beginning from Google and use some stuff from IBM, you can do that. And yes, the last line was, I said just before, it's already a business reality, especially in chemistry, in problem of scheduling in industry, in factories, for example. And everything related to combination, optimization of combinatory. So we saw a bit superposition, we saw measure, the two concepts that are connected. I hope you get them. Yes? And the third concept, quite important, is entanglement. Entanglement is the phenomenon, actually, where two particles form a band system. the two particles are able to work together. For example, if the first particle changes quantum state quite automatically is not the good word, but automatically the second particle is going to have the same state. It was a reason of scientific controversy quite a long time ago between Einstein and Niels Bohr. Einstein was thinking it was not really possible. There was something strange. The explanation for him was there is something we don't know. He named that hidden variables. There is something hidden we have to find to explain this phenomenon. And Niels Bohr was not okay with that, and they had a lot of intellectual debate about that. No, not a fight. They respect between each other very deeply, and they were friends. But on this point, they were not okay between them. And there was a famous article, EPR article, where Einstein, the E is for Einstein, and two co-authors, P and R, I don't remember their name, explained that there is hidden variables, actually. And the mind experience it did, it's, for example, if we have two particles very far away, so far away between them that you cannot easily go from one to the other with the speed of light. We should go much quicker than the speed of light. It's mind experience which is in contradiction to have these two particles in entanglement. It was the argument of by Einstein, but it was wrong actually. Perhaps you know the famous sentence. Einstein said something like, "God doesn't play with dice." It was about that. It was about entanglement. Einstein said it's an obligation to have hidden variables. So God cannot do that. And that Bohr would have answered that, who are you, Mr. Einstein, to say to God what he is to have to do playing dice or whatever. And it was the big debate before the Second World War. And after the Second World War, there was a first results. It was not an answer, but Bell, a physician, find that if a result, Bell inequalities, if they are violated, there is no hidden variables. So Bohr is right. So in that case, he found an equivalence between entanglement and these mathematical results. And a few years afterwards, there was an experience with two particles distant about. We can continue. Yeah. With two particles with a distance between each other about 11 kilometers. And they proved that Bell inequalities were violated. So there is no hidden variables, and consequently, there is entanglement. There is entanglement. It's like that. It's the behavior of quantum world. And an application in quantum computing, it was done quite a long time ago, 10 years ago by China, a quantum teleportation, the transmission of variable, of data actually, by this way, teleportation, and with a satellite. It was done in 2012, I think. and he used deeply entanglement. Um, yeah. So I would like to present that. I will stay on my slide actually because I cannot connect to this website, but I will explain everything. So if you have these three concepts, measurement, superposition, entanglement, you are ready to do what you want in quantum computing and use a solution like IBM, but you can use the Atos French-European solution, which is really good, and which is European and French, it's really good. And you can use Google, you can use what you want, and it's quite user-friendly. So the point is to get these three concepts. Afterwards, it's not really difficult. You can create your circuit only in graphically, without coding, without really coding. IBM is really cool because you can do everything in the cloud. It's free, and you can access to queues of a large number of simulators, but of real quantum machine too. You can do that. You can do your algorithm and just send it to a real quantum computer, and you get your result a few minutes afterwards, as soon as it's your turn. It's an example with IBM Qiskit. Just a result, the bell state, it's the same bell than before. It's the maximum 2 qubits intrication, and don't pay attention too much to equation, but these 4 states is for maximum intrication entanglement. Intrication is entanglement for 2 qubits. So one of them is this one, the first one, and the quantum circuit to do that is this one. And Hadamard gate plus CNOT gate. After measurement here, we will get something in 0, 0 or 1, 1. 0, 0 because there is an intrication, there is an entanglement. The two particles has the same value, and we can check that after measure. Or 1, 1. So, you remember with 2 qubits, we have 0, 1 after measure, 1, 0, 0, 0, or 1, 1. In that case, we should get only 0, 0 or 1, 1 because the two particles are entangled, intricated. So it's the example of the code. This code can be done totally graphically with IBM. So it's quite simple to get. It's done in a Jupyter. It's not an obligation, but it's done in a Jupyter notebook. And you can, if you do some Python, you see, I have an import of NumPy because it can be useful. So it's Python-like, actually. We design a circuit, a quantum circuit, with 2 entry and 2 outputs. On the first line, we add the Hadamard gate. We have the CNOT gate between the first line and the second line. Here, there is a duo of the circuit. I get that. It's not it's awful. It's not very nice, but it doesn't matter. We can recognize on the first qubit Hadamard, between the first and the second qubit CNOT, and the 2 measure box. This circuit is it's exactly the same, but it's much nicer. And afterwards, I can send that to simulator or to a real quantum machine and to get some result. Remember, we are in a probabilistic world, so there is no sense to send this program runtime because it's probabilistic. You have to send that 1,000, 10,000. In theory, we should have no 0, 1 and no 1, 0. It's the case, good news. But here we should have exactly 50% for 0, 0 and 50% in 1, 1. The reason of that, of this approximation, it's because we sent only 1,000, so 10,000, 1 million would have get much precise results. And it's linked with, here it's a simulator, but with a real machine, it's related also to a big subfield of quantum computing. It's the management of the error. The error in the measure, there is a lot of stuff about that. It's possibly the main occupation of this field today. It's try to identify mistake, difference, and try to recall that and to have something relevant you can trust, results you can trust. I wanted only to propose that because there is no big interest of this circuit like that, but I wanted only to precise quite useful in a huge number of applications, and you can see here our maximal intrication here. Our circuit is here. It's the circuit of teleportation. Here I have a value I want to send here, possibly at 10,000 kilometers, and I have an intermediate qubit here, and the first operation is to intricate this qubit with this one. Here it's Alice, here it's Bob. Bob is wish to receive the value from Alice. And so it's not an interesting circuit for itself, but it's used in a lot of applications. That's why I don't know if I'm late or early.
I think you're actually early.
Yeah. Yeah, perhaps you have question or discussion. Yeah.
Yeah. Thanks for your presentation. I would like to ask some recent news. What is the hardest or the largest algorithm that is currently implemented for quantum computing? Like, what is the? Hello? Hello?
Yeah. Yeah, I can. So your question was, what is the
largest or hardest algorithm that is currently running on quantum computers, like some factorization or some simulation of some large system?
Actually, there are a lot of answers to your question. First, on real quantum computer, it's still on the field of research. For example, the real computer from Google in 2019 was 40 qubits. There were a problem with 1 qubit. They made the experience with 39 qubits, and it's really research with very cold atoms at minus 273 Celsius degrees. So it's challenging. But in the same time, we have quite a lot of applied quantum algorithm for industry. and it begins to be huge. But I guess your question was perhaps much oriented to cryptography, perhaps, with
I don't know the field where we have the recent news.
I guess that recently there is a topic, it's not an issue about what is named post-quantum cryptography. And it's from something named Shor algorithm. It was done quite a long time ago. I'm going to try to explain that you know, when you have a big integer, you want to get prime factors of that. It's a quite long problem to fix. It's in time complexity is not polynomial, so it's the reason it's used to secure banking exchange and your banking card, etc. It's done with prime factorization of big integers.
Yeah.
So
the question was how big that integer that now we can factorize. Is it known? Like, is it public? The number, the biggest number that can be factorized, let's say, on real quantum computers. How big is it?
it can be, I don't know exactly for this question, but what I know is the algorithm in quantum is polynomial. Yeah. So you can no. It's still not theory because it was proved also on real machine. So practically, you can have every interbanking exchange breaking because of that.
Okay, thank you.
I'm not sure to have answered precisely to your question, but we can discuss much later if you want. Yeah. Yeah.
Well, is it currently possible to make quantum simulations, not just molecular simulations, but quantum simulations on IBM quantum computer?
You mean open API?
Yeah.
It will cost you a lot of money.
Could you repeat? I'm not sure to get your question.
Can you use quantum computing now? Like, can you use IBM resources?
Yeah, well, in that case, I need my computer, or if you want, we can see that just afterwards together.
Now it will be a little demo, right?
Yeah, okay, yeah. So, it is the IBM Quantum Qiskit in cloud. You can create an account, it's free. It's the same to have the framework on your machine and afterwards to solicit a quantum solver, a real machine or a simulator, it doesn't matter. And it's the reason you have the API token here. Is you are from your machine, you declare your API token and you can target the solver you want, the simulator you want. So I don't use too much in the cloud. I use from my local machine, but it's quite amazing. You can have the composer. It's the graphical version. The graphical version of a quantum circuit. You see here you recognize the Hadamard gate, the CNOT gate, the two measure, and in the same time you have the generation of the code here on the right in kind of standard. Every platform has its own language, a kind of Python for every one, Google, IBM, etc. And there is a kind of standard. It's not really a standard named OpenQASM, and you have the generation of that in that language. So he's able to understand it is an intrication. For the moment, I didn't send anything to a solver. I should probably click on setup and run your circuit. And here, I only have to search for a solver. I'm not sure I have a good network because I have nothing here. I will try to. Yeah, I am connected, but I'm not sure. I'm going here. It doesn't matter. So if everything was okay, here you are here. You can choose you can choose your simulator and you get the result. It's the first version to begin to program. The second one is to use a Jupyter notebook online. For example, this one I did yesterday. I hope it's going to work. It's my, there is only one cell, but you can organize your code like in a Jupyter notebook, cell after cell. And it's exactly the same code. Here I declare the simulator. I begin by that. Here I create my circuits, Adamar gate, CNOT gate, the two measure. Here I have an execution 1000 times. I'm supposed to get the result and I can display some result. The interest to have a Jupyter notebook, you can use every libraries you like, NumPy, Matplotlib, everything you want. And afterwards, I think I can run here, run all cell, and yes, here I solicited directly the QASM simulator. Is more or less the default simulator for IBM. There are hundreds of simulators, and there are some real machine. You can choose the machine, the real machine, not so far away from your position. Try to identify where they are not too much solicited, and you can get a result quite immediately. Sometimes you can wait 1 hour, 2 hours. It depends the queue actually. And here is the result. So 0011 entanglement, no 01, no 10. And yes, I asked for display the diagram. Yeah, I encourage you to create an account and to begin to play with that. It's really accessible. I think the only condition is to get the three concepts before beginning: superposition, measure, connection between these two concepts, plus entanglement. Other questions? Yes?
Entanglement can disappear and appear again, yes? Can entanglement disappear and appear again?
I'm not sure to understand.
For example, in this circuit, we have 0, 0 and 1, 1. What happens if you got 0, 1? What does it mean?
It can be entanglement also.
So the entanglement breaks for some reason.
The entanglement is broken by the measure, actually.
So it's only, you can do it only once. So to transfer 1 megabytes of data, you need 1 million entangled particles. And then if they spend, He will not return, yes?
I'm not sure to understand the
For
last.
example, you said after measurement, entanglement disappears, yes?
Yes, yes, because entanglement, it's a kind of connection between two particles in the quantum world. So when we have superposition. After measurement, it's usual bit. It's our world. It's mechanical, Newton mechanical world. So it's 0 or 1 for each qubit.
Okay, and how can we do many measurements? So each time we need to create entangled pair? Create entangled pair each time for each measurement, yes?
Yes, for example, in that example, we run 1,000 times the program. So for each instance, for each 1,000 times, we add two entangled particles, two entangled qubits. For each qubit, we have superposition, and superposition were equivalent between the two qubits. So we know that it can be with this circuit, the goal of this circuit, Hadamard plus C naught, is to have superposition between 0, 0 plus 1, 1. It's the goal of Hadamard plus C naught. With Hadamard plus C naught, the superposition before measure is 0, 0 in bracket notation, 0, 0 plus 1, 1. And after measure, it's only 0 for the first qubit and 0 for the second qubit, or 1 for the first qubit and 1 for the second qubit. Because before measure, they were entangled. But after measure, it's the real world.
Okay, so the size of machines with quantum, it's large because we need to measure between to make sure it's entangled or not, or why it's so big?
Why it's so big? You mean in a simulator?
Basically, we see pictures of quantum machines. It's very big. Why it's so big?
Actually it's a physics machine. I'm not specialist of that, but it's a laboratory machine. Yeah, there is no combination needs for this real machine. But at contrary, if you try to design a simulator, you need to simulate this combination. If you have 3 qubits, you need to manage 8 states. 2 per 10, I don't know what is it, but perhaps it's 1 million. I'm not sure. So if you want to simulate that with your computer, you're going to use a large amount of memory because you have to manage this combinatory.
Okay, next question about no, I haven't noticed.
Thank you.
Other questions? Come on, you have to ask question now. Sorry. Okay.
I want to ask about real-world applications. In what cases is it better to use quantum computing versus classical computing?
When the first point I didn't insist on, but actually it's important, it's not magical. So if you have a problem to fix, you need to write a specific quantum algorithm. It doesn't exist. You cannot translate the the classic digital algorithm like that in quantum world. You have to work on that. So in which case, for example, prime factorization, the time complexity is probably not polynomial and probably exponential. It's the reason it's used in cryptography. And in quantum computing, it's polynomial. And in industry, so the first answer is when the complexity you get with quantum is better than in classic computing. It's the first reason. And the second thing I can add is now this time in 2023, there are some industrial players which use quantum computing because they don't use quantum to have a precise answer because it's not possible, but they use quantum heuristic and quantum simulator because it's much quicker than calculation on classic computer. And much quicker means in that field, industry means cheaper, actually. So it can be identification of this molecule in chemistry, this kind of problem, or optimization of fabrication in factories. You know, you have to schedule in which order your material is going, or I don't know in English, but this kind of stuff in factories, and it's optimization problem. For optimization problems, operation research, this kind of stuff, you can already have good results. And I'm pretty sure, for example, there are some consulting companies specialized in writing quantum computing, a quantum algorithm for industrial problems. And after that, when they are ready, they go to Qiskit, IBM in the cloud, and they get a solution, and they sell that to a customer.
It's not kind of ready. Probably it will be like in 5 years to real usage in areas that have probability heavily used, like financial predictions, market predictions. So it's like just going on now, but it will be first practical results that you can buy. Probably will be in like 5 years.
Yeah, and the problem about that is there is a kind of opacity because there is something connected to geopolitics and sovereignty. For example, there was last year a huge military plan in France. There is perhaps 20% of this plan in terms of euros dedicated to quantum computing. So in this configuration, so there is something like secret culture. If you have something like that, capability to predict a lot of stuff in the financial field, you're not going to tell everybody, I have that. If you're interested, you keep that for you because it's really powerful. So perhaps there are some countries, some companies, very advanced, much advanced that you can guess actually because there is a kind of opacity in communication about.
And are there any applications in AI? Are any experiments being done?
I'm not a specialist, but I attended several presentations about that, machine learning and quantum computing. It was with IBM. So final results were not amazing, but we can suspect a bit like you said that in a short future it's going to have something relevant with that. For an example, in IBM Qiskit there is something dedicated to machine learning including NLP, for example, with quantum machine in the framework. So there is a volunteer, there is a strategic direction, at least at IBM, but so I think rapidly the answer is yes.
Thank you.
Thank you.
Other questions, please? Yes, just a second.
Немножко выйдите сюда. Сюда влепите, чтобы там под динамиком.
In one slide we saw that zeros and ones have different probabilities. So zeros have slightly more and the ones have slightly less. Is it always like this? So there's always you got 0, 0 more.
Actually, for example, if you have 1 qubit, you have 2 values, 1, 0, and 1. And you have a combination, a kind of linear combination between these 2 values. It's not exactly probability, there is a square 2 somewhere, but it represents probability for each items, 0 and 1. So for 1 qubit, the quantum state before measure is probability to be measured after much later of the first value, 0, plus probability to be measured of the second value, 1.
Can human influence on this result with its will?
On simulator, no. But the good thing, I forget to mention that, the good thing, you are not supposed to know the exact value of superposition before measurement on a real machine. Because to know the exact value, you need to measure, so you interrupt the superposition. So a good way to learn, it's to use simulator, because with IBM Qiskit, it's a simulator, so the algorithm know everything and know the current superposition. So it's a good way to use simulator, because you can know exactly what's happened at each step, and you are not supposed to know that if you were working with a real machine.
So this simulator is not a real machine yet?
It's not a real quantum computer. It's a simulator able to simulate the combinatory, the superposition. So it needs a lot of memory, because for 3 qubits, it needs to simulate 8 states, etc., etc. For example, if you want to simulate I don't know, exponent. Yeah, it's too big. 10. I will try with 10. I will try with 100. It's crazy. I will find something like 20. Yes, you have 20 qubits. You want to simulate 20 qubits. It's easy to program. Yeah, you have to simulate every possible state before measurement. 2 exponent 20, you have 20 qubits. It's 1 million. You need to, at each step, to simulate 1 million. 1 million possibility. So it's exponential. It's not rhetoric. It's really exponential, and it's the reason because industry and everybody is interested by that, because with only 20 qubits, you can access to a combination of 1 million of states. And if I if I wrote something like that, it's crazy. I'm not able to name this number. And possibly it's bigger than the number of particles in the universe. So we can feel the power of this technology. And it's not, it's possibly a bad news, actually. Yeah.
Thank you.
Thank you.
Any other question? Okay, then thank you very much, Benoit. If you want to add something, when we can conclude.
Yeah, thank you to attend the presentation. Questions were really interesting, and
this IBM, sorry, can I open account and
yes,
play with it? It's free.
it's free. It was absolutely totally free until last year. It's still free, but for some real quantum computer, it's you have to pay. But you can learn a lot only with this tool. You can learn a lot on your own. And I tried to design this presentation. But English is not my first language, so it was a bit difficult. But I tried to design the presentation with ideas and concepts I would have got when I began with quantum computing. And I tried to provide that. I don't know if I managed that. To get the minimum to be able to work with autonomy and to work alone without wonder about conceptual creations, and yeah, try to provide.
Yes. We see it physically, like how can I try something, of course. So we encourage everybody to open account and play with quantum computing. Try to implement some algorithm or something.
Yeah, and
it will be very primitive. But
I'm joinable. I think with the conference, there are my details somewhere, and yeah, feel free to send me an email or to ping me on social network. It will be a pleasure to help you or to discuss about that.
Okay, thank you very much.
Thank you. Thank you.